Good afternoon and welcome to Johnson Space Center in Houston and the STS-133 update. We have with us here in the room today to tell us about Discovery's preparations for launch, Shuttle Program Manager Shannon and Space Station Program Manager Mike Suffredini. But we're actually going to start today's briefings with comments from...
There's been lots of ups and downs through the process, but the team has really hung in there. They've really stayed focused on what they need to do. They spent quite a bit of time over the holidays doing some activities. We did an external tanking test out at the launch pad with instrumentation on the vehicle. We learned a lot about how the vehicle performs during loading, and John will talk to you about that in more detail in a minute. We've also done lots of offline testing in New Orleans. We've done some offline testing at Marshall Space Flight Center. And that testing has been invaluable to lead us to where we are today and where we think we understand what the problem is on the tank. We understand what the work is in front of us to get the tank in a flight-ready configuration and get it ready to go fly. So we'll spend some time with you today going over kind of the thought process. We'll explain to you what failures we thought we saw early on, which ones we found later, and then how we ended up with the situation where we are today. And it's really a complicated factor that leads to the problem we see in the tank. We think it's really a combination of materials deficiency in the tank. Fracture toughness parameter isn't exactly what we wanted, and we didn't really specify that parameter, but it's not quite as fracture tough as we would like, and fracture toughness is just the ability to resist a crack once it starts in the material. We'll talk about that, but that alone isn't enough to cause the problems we're seeing on the tank. It's that and some tolerance buildup, and the combination of those yield us the problem that we've got. And John will explain to you again what the overall process is of how we're going to go ahead and repair the tank, get it back in a known good configuration, and get ready to go fly. So I think the encouraging thing is the teams kept working through this. They stayed curious. They kept looking for problems. When we rolled back to the VAB, we didn't really have to go do that, but we wanted to do that just to make sure we could x-ray the backside of the tank and not see any problems over on that side, on the LO2 flange side. We did that. We discovered a couple failures over there, and then that made us think that, hey, maybe the failure mode that we had postulated before wasn't exactly right. We've refined that to the failure mode I just described, and we're essentially ready to go forward. So again, we look forward to your questions afterwards. John will give you kind of a detailed overall briefing. And when I include the team, then Mike Suffredini will talk to you a little bit about what the manifest planning is and how the space station is getting ready to go receive the shuttle. So we'll give you pretty much an end-to-end briefing overall. I know you may have some questions about STS-134 and Mark Kelly's flight. I think out of respect to the family, we really are not ready to answer those questions today. We're going to let Mark decide really kind of what he needs to do. We'll let his personal situation take focus on his activities and his thoughts. And later, when we know more about where STS-134 sits and what our options are for Mark and his activities, we'll come talk to you at that time. So we really won't answer any questions about that today. But and again, I think we'll do that out of respect for Mark and what he's dealing with. And our hearts and prayers go out to the family. And we're really thinking about Mark in everything we do. So with that concludes my opening remarks, and I'll turn it over to John, and he'll give you a kind of a rundown of what we've been through in more detail. And thank you.
Okay, thanks, Bill. That was a good summary. Let me review where we left off the last time we talked to you. Of course, this initial problem occurred on November 5th, and in the 2 months since that happened, we've done a tremendous amount of work and come a very long way in our understanding of the problem and how to get this tank to 100% confidence level. When I left you, we had 2 cracked stringers on the inner tank LOX flange area. We showed you the cracks, and we had gone through a very rigorous fault tree analysis. And it left us really with 2 potential causes. The first one that we talked about was a gross tank problem where it was just not assembled correctly, and you could be having a buildup of stress in the skin once you loaded it with liquid oxygen, and it could cause the stringer cracking. The other one was that we had a more localized problem, and it was assembly stresses that were built up when the inner tank was manufactured. And when we put the cryo load on it and bent it, then it fractured. So we did two things pretty much immediately after I talked to you the last time. First is we went to MAF and we reviewed the assembly process of an inner tank. And let's go to chart number 1 here, and I'll just orient you on what an inner tank looks like. This is the exploded view of one inner tank panel that would be located next to a thrust panel. And the very back piece is just a thin sheet of aluminum that is the covering member. On top of it is what's called the cord, and that's a very strong, rigid, curved piece of metal. If you look at the cross section, it'd be an L shape. That's what's actually bolted to the flange on the liquid oxygen tank. So that is where the load is transmitted from the oxygen tank to the inner tank. And that's really the area where when the liquid oxygen tank shrinks radially by about 1/2 inch, it's that cord actually that is shrinking, and it's pulling the tips of those stringers in. Next to the cord, you can see we have what's called a tapered shim spacer. And as the stringers are coming down the skin and then they go up onto this L-shaped cord, they make an angle on the bottom, and that shim is there to provide support for that initial angle as it runs up to the cord. One of the things I'll talk to you about in a minute is where you could have assembly process issues. That tapered shim spacer, as you can see, is just a one piece going across 11 different stringers, and it is not custom fit to each stringer, so you can potentially build up assembly stresses there. On top of that, you have 2 sets of doublers, and the stringers go on top of that, and they're fastened down. The way it's built up is the entire midsection of the stringers are riveted to that skin. In the areas where you have the doublers and the shims and the cord coming up, those are hand match drilled and then put in with fasteners with about 5,000 pounds of preload, so very, very strong fasteners. So we went to MAF and we looked at it, and I got to tell you, when we looked at MAF, the gross tank issue really, it did not seem very credible. When you look at the jigs and how it's set up, and when you put the LOX tank on the inner tank, it would have been very obvious when it was being built if there was some gross problem. But when we looked at the buildup of the stringer panels, we said, you know, there could be some assembly areas here that could potentially cause us a problem. And the forensics of the stringer pieces that cracked and we took off tended to support the assembly stress theory, because you could look underneath the feet of that stringer and you could see some foam intrusion, so they were a little bit lifted up. In some of the holes that had been drilled, you could see some material from the drilling process was under there, so you had a little bump that you were putting that fastener over, so it made a lot of sense to us. Then we performed the instrumented tanking test, and this tanking test was a tremendous effort by the team down at KSC to go to panel 2 where we had these failures, and panel 3 to get a similar panel, put strain gauges, put thermocouples. We put 15,000 dots on the outside of the flange, looked at it with photogrammetry cameras to look at flange rotation. And we did the tanking test, and it showed to us that the gross tank piece of the fault tree was not correct. That we could rule that one out. The loads and stresses were very linear. They agreed with the models very well. There was no real difference between panel 2 and panel 3, so the tank was behaving as appropriate. So we were down to one scenario on our fault tree, and that was the assembly stress. Then, kind of in the week between Christmas and New Year's, 3 things happened. The first is that we rolled the vehicle back to X-ray, but also because we were going to put these radius blocks on top of the doubler stringers. And I'll talk about radius blocks a little bit more and why we think that's a good idea. So we rolled back and we did our X-ray, and we found out on the back side of the tank that we had 3 additional stringers with cracks. 2 of them were not on the doubler. So that made us kind of think a little bit that the hypothesis that the tapered shim spacer that's only under the doubler that could cause your highest uncertainty for assembly stresses, that may not be exactly correct. The second thing that happened is that we started trying to test our theory by taking stringer sections and putting them in a test rig where we could bend them down and get cracks like we had in flight. And what happened was we put washers, we put safety wire, we put all kinds of things underneath those fasteners and fastened them down and tried to break them, and we could not get them to break in a flight-like manner. And so that made us also think about, hey, maybe you don't have the whole story figured out here. And then the third thing that happened in that week is that we tested the removed stringer pieces that we had pulled off the tank for strength. And the strength in the tensile pull tests came back above our minimums, but it was a little bit high. And that made the material science guys think it shouldn't be quite that high. Maybe we're trading strength for ductility, and we're getting a more brittle material here. So they ran fracture toughness tests on it. Basically, you put a certain amount of strain energy in it. You see when it will break. You also see what type of crack growth you get. If it's a small area of deformation that will crack and then arrest, and then as you continue to deform it, you get further areas that crack and arrest. And that's not really how this material behaved. Under a load, it cracked, and it cracked to relieve almost all of the strain. So you had crack growth that was a little bit unexpected as well. Let's go to picture number 2 here. These are the stringer cracks that we saw with the X-ray, and you can see that along the feet of the stringer, very hard to tell, but it's just little hairline fractures along the feet, very similar to what we had over on panel 2. It was on 1 foot on stringer 6, 1 foot on stringer 7, and then both feet on stringer 11. The interesting piece is that stringer 11 was also over a doubler, so a little bit of the theory of assembly stresses were involved in this failure was still hanging in there. So when we took a look at the tensile material that we tested off of the stringer, the team noticed that the appearance of it was different than the material that we had been testing before, the stringer material. And let's look at chart number 3. This is what we called a mottled appearance, and it just you can just see it looks rougher. It looks just a little bit different, and that made us go look under scanning electron microscope at fracture planes, and we actually think what was occurring here that caused this mottled appearance is a little bit different grain structure that could be caused by a different heat treating of the material. So you actually changed the properties of the material where it became more strong but less ductile. And that is directly off of the bottom one is directly off one of the stringers that initially failed on 137. Okay, that's probably enough of looking at modeled stringers. Okay, so what did we do here? We said maybe assembly stresses wasn't it. We've got this material that is got lower fracture toughness. And when I say lower, it wasn't dramatically lower. It was about 65% of the fracture toughness that you would expect for this aluminum lithium alloy. And when we tested the material, of a stringer that had this lower fracture toughness in the test rig, it still was able to carry loads that were greater than what you would see during cryoloading or during flight. So the lower fracture toughness wasn't the complete answer. The other piece of it that is kind of interesting is that when we looked at how many stringers potentially we had that may have this lower fracture toughness by looking at the lots and the heat treat code on them, it turned out to be about 78 of the 108 stringers on the inner tank potentially had this lower fracture toughness. And of course, we loaded it twice with cryos, and then we X-rayed it, and we didn't have 78 cracks in it. We had 5 that had cracks in it. So that said that it wasn't just fracture toughness; it was a combination of different components that gave us the cracks. So immediately we went off and we went to ET-139, which was partially built at Michoud, and we sectioned off stringers on their panels just as built. And we put them in the test stand that would replicate the loading you'd see during cryoload. And finally, on our New Year's Eve test, we're able to replicate flight-like cracking. And that's the next picture I have to show you here. You can see right by the fasteners, you've got the small crack running down the foot of the stringer. And this was a big moment for us because we were able to show that we could crack the stringers with this low fracture toughness material, very similar to what we were seeing on the vehicle. Now, to cause this crack, it took a loading about 2.5 times what it would normally see in any cryo loads or flight loads. But remember, this is a low fracture toughness stringer that had no assembly stresses built into it at all. So that was good news to us that we were able to do that. And finally, starting to home in on the problem and the cause, then you can start looking for the answer. We looked very hard at the loads on the tank to see if the cryo loading itself gave you a sufficient screen for flight loads. And it turns out for the first 3 fasteners on each stringer, that bending load that you get is greater than any loads you would ever see during flight. So you're covered for the first 3 fasteners. Fasteners 4 through 8, you see about 85% of the load you would see during a flight load. So the cryo was not a complete answer to being a screen for your flight loads. So that meant that we had to march down the path of doing some kind of an action to increase our capability and make sure that we could handle the flight loads. We should talk about exposure to risk a little bit here, and the concern we had was really twofold. The first was that you could potentially have a crack in both feet of a stringer, just like we saw on the pad when we loaded on November 5th, and that it could be a significant enough crack to allow the stringer to pop out and to bring some foam out. And if that happened at the wrong time during ascent, you could lose foam, and then you'd be at risk of hitting the vehicle. That was one of the worries. The second worry was that if you had enough of these stringers that had a problem in a row, then you could end up having a structural localized buckling of the tank, which of course you would not want. Now, how likely is either one of those things? Well, we talked about that as a team, and of course, since you did cryo load twice and you've loaded up the first 3 fasteners to above what they would see during flight loads, you're not going to see anything during flight in those first 3 fasteners. Then it was a discussion of, well, could you have a problem, fracture problem, between fasteners number 4 and 8, the next 4 inches of the top of the stringer, that wouldn't be exposed during cryo and subsequent x-ray, but would be exposed during a flight load and could end up propagating up the stringer and causing the foam to come out. And that was a very difficult problem to quantify. From the structural standpoint, what we got through analysis is that it would take more than 3 stringers to fail in that manner in a row. So you need 4 at least to fail in a similar manner to end up having some kind of a buckling problem. Much lower probability than having a single one, but again, it's hard to quantify. So where did that leave us? Probably at a low risk, but it's hard to quantify because we have that lower fracture toughness material on most of the stringers on the tank, and it's very hard to tell where your assembly stresses are. You can't really tell that through x-ray. So what we decided to do was that we can get rid of the whole discussion by putting in these things called radius blocks. Let's pull up the next chart. And you can see, let me orient you on this picture, the big kind of tapered L piece is the cord that attaches to the flange. And you can see the stringer running on top with those fasteners going through it into the cord. And then the radius block is a small piece of 2024 aluminum. It's about 6 inches long. It's about 1/5 of an inch thick. And it's curved. That's why they call it radius. It's curved to kind of go up the side of the stringer. And it's fastened down right on top of the feet of the stringer over that cord in that shim area. And all it does is it keeps the feet of that stringer nice and flat, so you don't get bending as you start to bend down the stringer itself. You're not starting to bend up around those fasteners, which causes the localized stressor. It keeps it nice and flat, puts all the bending stress up into the top of the stringer, which has much greater capability than the feet do. So by just putting this very small piece of aluminum over the top of that cord and keeping those feet nice and flat in that area that bends down, you increase the capability of that area by about 3.5 to 4 times. So it's a very simple elegant fix to the problem. And if you think about it, you've got this 22-foot long stringer. The top foot of it bends and rotates as the tank is initially chilled, but the other 20 feet of the stringer down the middle, it's just in tension and compression load. So this material, the strength properties are very good on it, so that tension and compression in that stringer is good. If you can fix the top part with this radius block to handle the rotation, then you're in really good shape, and you have an inner tank that you have full confidence in. Now, the other thing we've looked at very hard is on the LH2 side, because of course you're attached at the bottom on these stringers to the liquid hydrogen flange. It cools down, but it cools down differently because it's at the top of the tank. It's a much more gradual cool down of that area. You don't have the immediate compressive loads and the bending loads on that area. And since the loading path is so much different, we anticipated through analysis that we would not have any problems on the liquid hydrogen flange. And we finished X-raying 88 of the 108 stringers back in the VAB, and that kind of showed our analysis was correct, that we don't see any cracks and we don't anticipate any problems at all. So it's been a long road. We're continuing to test. Let me pull up the last chart I have. We built at Marshall Space Flight Center a very ingenious testing rig where we can mount a stringer, and we can put the 3 different forces on that stringer that it would see during a cryo loading event, and we can actually overstress them in some cases. And the 3 loads it gives you is the downward load on the stringer, of course, mimics the bending because of the tank shrinkage. The rotation load at the tip of it is as that flange starts to rotate in because the tank shrinks and it gets weight in it. And then the compressive loading is as you fill it up with liquid oxygen. And of course, that's a large weight on it. And what we can do is we can put stringers into this test setup. We instrument them exactly like we had them instrumented on the tanking test to make sure we have a good one-to-one comparison. We're testing the old material, we're testing the new material, we're testing with flaws, we're testing with radius blocks installed, without radius blocks installed. We check the stiffness of the structure. We can test everything on it and verify that, yes, we have shown exactly what happened on ET-137. Yes, we have shown that the fix that we have proposed with the radius blocks is very effective, and it does not allow cracking during the load cases, and it brings your factor of safety up exactly where you want it to be. It's just too hard with this lower fracture toughness material, not knowing where all the assembly stresses are, to estimate what your factor of safety is in the tips of these stringers. So we're just going to bypass all of that by putting these radius blocks in, and that brings our factor of safety up to an acceptable level. This was a tough problem, and the guys at Michoud and at Marshall have done a terrific job. You know, they worked through the fault tree. They had a hypothesis, and when it was not panning out that it was just assembly stresses alone, they kept going, and we rolled the vehicle back. We did the X-rays. They did all the testing of the remnant material that we pulled off the vehicle. They found a new hypothesis. They've tested it out, and they have full confidence. We briefed this to senior NASA leadership yesterday, and the engineering teams at Kennedy, at Marshall, at JSC here, the prime contractor on the tank, Lockheed Martin, they're all in sync with our fix. They agree that we're on the road to bringing this tank to 100%. So it's like I said, it's been 2 months of very vigorous activity. It took a lot of investigation to kind of piece the different components of how this could be happening together, but I'm very confident that we've finally got it figured out, and we have a fix that is easy to implement and will be 100% effective. So that was a good news this last week. That's all I had. We can talk about launch dates with Mike.
Good afternoon. I won't spend quite as much time with you. The shuttle program, as a result of what John talked to you about today, told us that as a community they would be ready to fly as early as the 22nd of February. And as you recall, when we talked to you before Christmas, we told you that we had actually assessed 2 windows for this flight. One was the early February window, which we were attempting to make when we chatted with you before. But we also were considering this later February window. So once our shuttle program colleagues got to the point where they felt comfortable with the repair and the date they thought they could make, we went to look to see if we could open up the window, the late February window, any to give us more opportunities to launch. In doing that, we, working with our colleagues both in ESA and JAXA and our Russian colleagues, we were able to come up with a plan that allows us to launch a little bit earlier. Originally, we told you that the launch window was the 27th of February to the 6th of March, and it closes it closes in time to have the shuttle depart before we do our crew rotation in mid-March. So we looked at if we could pull it up any earlier, and we think we can support a launch date of the 24th of February. And what this causes is we were launching the ATV already on the 15th of February. And it takes about 8 days to get to ISS on a normal plan. The reason why we were shooting for the 26th of February at that time had to do with conflicts we had with HTV. And it also protected 3 or 4 launch opportunities out of French Guiana. And so if we launch on plan on the 15th, our normal flight plan of about 8 days would put us at ISS on the 23rd. And so working with the shuttle program and ESA, we accepted that that was a reasonable risk to take. So if we delay the Ariane launch for whatever reason, it potentially has an impact on the shuttle launch, but that's several days before we launch, and so we can just slip along with the ATV. Now, in addition to that, our Russian colleagues had an EVA plan for the 21st of February, so that's only 2 days before the ATV docking, and there's quite a bit of work to set up and test out the electronics system that is used to communicate with the ATV. So in working with our Russian colleagues, they'll set up those systems prior to the EVA while they're also doing the EVA preps, and do the majority of those checkouts before the EVA, and then go do the EVA, and then be ready for the ATV docking. And finally, our JAXA colleagues are affected because the normal on-orbit stay time for the HTV, well, we normally plan for 30 days. They can extend that up to 45 days. They're having to extend that up to 60 days in order to allow us to have the HTV there through the whole ULF-5 flight, which allows us to get the payloads off of the HTV and onto the pallet that comes up on ULF-5. And also there's an exchange of some racks from the permanent module that we're bringing up on shuttle. We're rearranging things. We have racks coming up on the HTV, and then racks that we want to dispose of with the HTV. So this allows the HTV to stay, and we can do our nominal, roughly speaking, our nominally planned mission with those 2 vehicles. And so with that, they'll be departing about the 28th of March. There's still some work to do in order to finalize all this planning that we've done over the last several days. We have most of this information because we'd already started some of the early work as we were considering this later window anyway. And so over the next several days, we'll finalize that. We have the HTV launch here in about 9 days. They have their flight readiness review on the 14th. We are finalizing our analysis for a meeting that we're going to have on the 12th, which is sort of a delta meeting to our flight readiness review for that HTV flight. So we'll firm up our analysis, and then at the flight readiness review, or at the JAXA flight readiness review on the 14th, they'll confirm the 60-day stay, which is going to be relatively easy to accomplish. They just had to complete some thermal analysis. And then with that, we'll launch the HTV knowing that it can stay the 60 days. So that plan works, and we have, in fact, today at the SSPCB, we put those actions in place to support the 24th launch date for the shuttle. And so with that, that concludes my comments.
Okay, we are going to start with questions here in the room. A few reminders, though, before we do. After that, we'll go to the other centers in Foam Bridge. But first of all, remember to state your name and affiliation and try to direct your questions to the briefer that you'd like to answer it. Also, as we mentioned at the top of the hour, the focus of this briefing is STS-133, so we'd appreciate it if you keep your questions on that topic as well. And as we're limited in time today, and we have lots of reporters here and at KSC and on the phone, if you can stick to one question to begin with, then we'll try and get follow-ups if we have time at the end. I think that your colleagues will appreciate it. Okay, we'll start here with Mark.
Thank you. Mark Carreau for Aviation Week, and it's for John Shannon. And I'm going to apologize. I really appreciate your thorough explanation, and I really tried to follow it. I think I fell off the wagon a bit when we started out with potential materials and assembly problem, and I'm not sure exactly where your investigation brought you at the end, and so we can kind of say whether you do have root cause now, or you're close, or you think you do. Could you sort of address that, and does it affect the other two tanks?
Okay, that's two. We absolutely have root cause. And we have been able to show that through test, and it's a combination of two factors. It's the low fracture toughness of the material. You have about a 65% of the expected fracture toughness, combined with some assembly stresses that were built up in different areas. We know that because when we loaded the tank, we put high stress on all of those stringers that had that low fracture toughness, and we only had cracks in 5 of what we believe were 78 stringers. In looking at those stringers that had cracked, we're seeing the evidence of those assembly stresses that combined with that low fracture toughness to cause the problem. So we have root cause, and we have a fix that we're completely confident will eliminate those root causes. The impact to other tanks is interesting. The suspect heat treat lot, we believe, affected tanks 136, 137, 138, and then the pieces of 139 that are still out at MAF. So 138, ET-138, which is currently scheduled to fly STS-135, I expect it to have exactly the same issue that this tank has. And of course, we're going to continue to do testing, continue to understand our risk posture. Right now, I would say it's very likely that we'll do exactly the same repair on ET-138 that we're doing right now. 122 is from a different lot. It was built in 2000. The tanks with the stringers that we're concerned about, they were built with stringers that came in about 2002. So we think ET-122 does not have the exposure to this issue. That's going to be a little bit difficult to prove because we right now don't think that we have remnant stringer pieces that we can go test and verify that. So we're still talking about ET-122. I think it's possible that we'll end up doing a tanking test on it and doing x-rays on the orbiter side just to verify that there are no issues at all. There's still a long way to go on that discussion.
Yeah, Jim Oberg with NBC. Well, attaboys and attagirls around. That was a real fine piece of detective work. And glad you could still have the team people here to do that.
Yeah.
The big first question is, what's it weigh? You're adding material to it, so what it cost you in terms of payload?
From just a weight standpoint, I don't know. It's not quite 108 because we won't do quite all of them. The ones that have the repair, obviously. So there's probably 103 6-inch by 1/5 of an inch by about 3/4 of an inch pieces of aluminum that we're adding. So I don't know, less than 5 pounds, I guess. We'll get you a number.
Robert. Hi, Rob Perlman from collectspace.com. For John, since this will be a new configuration that with the radius blocks that you haven't flown before, do you need to do another tanking test, or how do you certify that modification for flight?
Yeah, that's through the testing process and the analysis process. The initial thought was that adding these small pieces of aluminum over that big, thick cord, which is a very stiff piece of structure, would not cause any kind of a change to the tank behavior. We're proving that out through test. We're looking at the strain, we're looking at the stiffness, and verifying in the test that material that does not have a radius block does not behave any different than one that does have a radius block. And we're going through and modeling that for the entire tank and verifying that we're not going to do any harm. Right now, it looks really good.
Eric Berger with the Chronicle for John Shannon. My question is just about sort of the nature of these radius blocks themselves. Until yesterday, I'd never heard of them. And they sort of seem to fit really well with what you're trying to do here in terms of these stringers. Were these something that you just kind of had sitting around in a warehouse somewhere? Were they machined, or what's sort of the origin of them?
The radius blocks are used in standard applications on the inner tank wherever you need some additional strength in the stringers, like wherever you have there's some cabling, there's some support structure that ties into areas behind some of these stringers, and it's been standard practice in the design in those areas where you needed that additional strength to put a radius block in there. Radius block is kind of fancy. They call it radius because it mimics the radius of the little fillet area going from the feet up into the sidewall of the stringer. So it's a curved little piece of metal on the sides, but it's really just a little thin doubler that you put on there to keep those feet nice and flat.
Ryan Korsgaard from KPRC TV for John Shannon. Given that this launch date is now set, is that April 1st possibility for 134, given your current situation as well as everything you've gone through for this launch, is that viable or even possible at this point?
Well, some of it depends on what we are going to do with the next tank. If we end up doing the tanking test and then doing the X-rays out at the pad like I expect we will, that will bring April 18th in as the launch date for 134. So we're still talking about that plan.
This is for John Shannon as well. Kevin Quinn from KTRK here in Houston. It's a question we have to ask, and I know you said y'all won't answer it, but we have to ask about what policies are in place when there is some question as to whether a commander can do what he needs to do for an upcoming mission. What plan Bs might there be to bring in another commander if necessary?
Yeah, as Bill Gerstenmaier said at the beginning, it's not the appropriate time to talk about that, and we'll just leave it there today.
Okay, I think we're ready now to go to Kennedy Space Center, where they've got a few reporters waiting for us.
Hello, this is Marcia Dunn of the Associated Press. John, this question is for you. I'm just wondering, as we approach the 25th anniversary of the Challenger accident, we've got a shuttle grounded again by technical problems. Is this like the total opposite of decision-making and policy that you would believe would have been in effect 25 years ago this month? I don't know, your thoughts on all this, please, as we approach January 28th.
Yeah, Marcia, I don't want to compare and contrast. I'll just say that I am extremely happy with how this team has approached this entire problem. I have felt zero pressure from Bill Gerstenmaier or Mike Suffredini to rush through this. As we have stepped through this entire process, we realized early on that we needed more information, so we went and did the instrumented tanking test. We got that data, said we still need more information because we don't fully understand the problem. So we rolled back to the VAB, learned a tremendous amount there. That was outstanding. When we started doing the tests and didn't get the data that we expected to get, the team sat back, and we had tremendous support from the engineering directorates and the safety organizations at each of the manned spaceflight centers. And we had help from the NESC, and it's just been a tremendous team effort. And we kind of get beat up a little bit because we've had a series of slips here. As we would learn things, we would move the launch date out. But it's only been 2 months, really 2 months and a week since this happened. And when I look back at all the work that has been accomplished with Thanksgiving in the middle there, with Christmas and New Year's. And honestly, with a workforce that is less than what it used to be, I'm just astounded this team was able to pull it all together and come to this point. It was a great effort, and we're going to fly with a lot of confidence in this tank. I think through doing the tanking test and the VAB work and the X-rays and just building our factor safety up with this very simple modification, we've gotten rid of the uncertainty in the discussion, and we're going to fly with a lot of confidence.
Bill Harwood, CBS News, and this is probably for Mike Suffredini, I'm not sure, but since we've talked about 133 and 34, can you tell us what the latest thinking is on 135, just a rough time frame? I realize with tank questions still outstanding, I don't know, there's no specificity here, but is there anything better than June 28th right now in terms of what you would like to do if you can get it done your way? Thanks.
Well, Bill, I think we mentioned this before. The preference, because of the way the vehicles line up and where the shuttle flights are here in kind of the early springtime, we would prefer to have 135 if we were to get it as late in the fiscal year as we can, just from a spacing perspective, and to make sure we have as many of the large ORUs on board as we can get. Some of them are being manufactured. We've picked up the pace on manufacturing some of our larger ORUs in order to try to make that launch date. And so our preference has been towards the end of the fiscal year. We've been kind of chatting about a late August time frame if everyone else can support that. So that's what we're kind of looking at.
Todd Halverson of Florida Today for John Shannon. Just a sheer amount of effort that has been required to deal with this problem brings up a question in my mind in terms of where you are at in your drawdown of the workforce. Kind of, if you could recap where you started in terms of the numbers of personnel, both civil service and contractor, and where you're at now, and equally important, whether or not you believe you have the personnel with the critical skills required to deal with this type of problem if you run into them going forward with the last couple flights.
Okay. So let's talk about our workforce profile a little bit. The program really, this is an oversimplification, but you can think of the program was composed of two separate workforces. You had the sustaining engineering teams and you had the operations teams. And what we have done is, as the last hardware is produced and delivered and integrated, we have laid off those teams. But we kept in each of the contractors a core of sustaining engineering. So the production went down, but the sustaining engineering we kept to be able to deal with things exactly like this. The operations personnel, they were kept fairly high because we were at a fairly rapid pace of flight, with a plan for how we would drop that workforce down as flights were completed. And so we're basically on the same workforce profile that we have described here for the last 3 years of planning. As production teams have really gone down to not many folks. Sustaining engineering for that production teams have stayed pretty steady, and they will stay steady throughout the remainder of the program. And the ops team, as different ops activities are completed and flights are completed, then we gradually draw that down to the appropriate levels. So this showed, I think, that we're doing it the right way, that we're keeping the right team around to be able to troubleshoot these problems. We hired back, because of the metal work that is required on the tank, we hired back, I believe it was 22 people that were previously either moved inside the Lockheed Martin Corporation or had gone out on the street. And they came back very happily and very willingly, and they're working down at KSC on the tank, and they'll be used on the whatever repairs we decide to do for ET-138. So, we stay in contact with the team members. I think there's a very high morale in the workforce, and folks just want to see this program end on a very high note and finish it right. So, even if folks have been let go, we were able to bring some back. We're also, able to keep folks around to the end of the program just to deal with these kind of issues as well. And we probably ought to shoot it over to Bill Gerstenmaier, both for the question on how this was handled in the workforce discussion.
Yeah, again, I would say it's a real tribute to the team that they've been able to stay focused on this problem and continue to work it. And as John described, when you get thrown a different curveball, the team just did a tremendous job of reacting. And it's not easy doing what John described, doing this balancing of trying to fly out this remaining flight out safely, balance the technical needs against the workforce reductions that we've been doing. And it's a tremendous tribute to the teams that they have done and supported all that activity as it goes forward. In terms of STS-135, we're going to change the focus a little bit. You know, we've been calling it STS-335, a contingency launch on need flight. We're going to start calling it now 135, and John will do that either this week or next week in the PRCB. And that doesn't mean a whole lot to folks on the outside, but what it means to us is we're kind of mentally shifting gears to where we're going to start thinking about STS-135 as a real flight, get our head back in the game, make sure that there's nothing we're missing from a manifesting standpoint, and we'll figure out the right time through that effort of when we want to go fly that flight. You know, as the manifest is laid out right now, it supports the June 28th date. We know technically Mike would like to move some things. We got to go look at the overall budget, look at workforce, look at staffing, and figure out the right location to put that flight. But you'll see us start talking about that flight as being more and more real. We're going to make sure we've got the tank ready. We make sure we got the workforce to support all the way through the end of June. We'll make sure we got the right training, the right plans in place. So you'll start seeing a shift to that from where we're treating it kind of as a contingency flight to actually we're going to start mentally thinking about it more as a real flight. So you'll see that over the next couple of weeks as we start moving through the program boards.
We'll go back to Kennedy now. Let's finish up there.
Kevin Oliver with WFTV in Orlando. I guess this question is for Bill. Following up on your mention of the budget, if they're talking about moving 135 to August, if you look at the bean counters, how much longer can the shuttle program continue? Do you have until October before you run out of time and money?
You know, that's not an easy question to answer. Right now, at this point, we have budget to get through probably through the April flight, as we just described, with margin budget-wise. We can get close to the June flight. We're going to need to see what happens with Congress and the continuing resolution. As you know, we're under continuing resolution until March 4th. We then need to get a new plan for what we won't need to do for the rest of the fiscal year. Depending on what comes in that budget, then that sets how much funding we have for the remainder of the year. So it becomes tough for us to speculate what funding we've got to go through. We can definitely get through the two flights. The third flight kind of sits a little bit on what happens and what kind of budget we get on that March 4th date. So we'll work that. We'll balance that as we go forward. But I think it's important that we start thinking of this flight as real and start doing the manifesting, the actual technical activities to make sure that this flight can be flown.
Hi, James Dean from Florida Today. John, just wondered if you could tell us when you're targeting completing these modifications and rolling out back to the pad. And I also just wondered if you, based on the materials that were used and stuff, if you thought at all or looked at all about whether it was possible this issue might have affected tanks that have already flown, and if you could have had a problem that went undetected.
Yeah. Okay, to answer the first one, that we, based on the start we did this weekend of removing foam in the flange area and giving the team the go for the repair, we think we'll be done sometime around the 23rd of January. I don't remember when we were going to roll out to the pad. We roll out pretty soon after that. That gave us about 10 days of margin contingency, either in the VAB doing repairs or out at the pad if we run into any issues there. So, and that's based on a launch day of the 24th. So we'll look at it closely. But we expect to be done sometime around the 23rd.
Okay, we're going next to the phone bridge, and we've got about 8 people and about 5 minutes left. So we'll start in the order that you called in, which means Denise Chow will be first.
Hi, Denise Chow at Space.com. I think it was in the last press briefing back in December, maybe that John Shannon either or Mike Suffredini said that with the delay they would need to do some cargo changes to offset some weight. And I was just wondering, since then, with this new targeted launch date on the 24th, has that changed at all? And are there any additional cargo changes that need to be made?
Sorry, Denise, can you repeat that? You've got some feedback in the background, and speak a little louder.
I was just wondering if there's any cargo changes that will need to be made with the new targeted launch date of the 24th. I think it was in the last briefing that they said the delay would need to offload some weight from the cargo.
Okay, if I understand the question right, essentially there is no cargo changes. We left the MPLM in the payload bay. We talked about whether or not we wanted to take it out and make some changes, but in the end we decided that we would stay in the payload bay. The one thing we were looking for is there's some cables that we were bringing up to allow the HTV vehicle to go on the zenith port, which is what we have to do now. We berth to the nadir port, and then we have to move it to the zenith port in order to let the shuttle come and dock concurrently with the HTV being there. That requires us to run a couple of cables up to the HTV. We had one cable already on orbit that we could use from another application, and we needed a second one, and we in fact have now designed that and are preparing to fabricate it with parts we have on orbit. So that resolved our need to get the cables out of the MPLM, and so we chose to leave it in the MPLM. So largely everything we had planned is the same, both in the MPLM, clearly in the MPLM, but also in the mid-deck. There might be one or two minor things that we change out for ascent, but it's nothing large. There's nothing really significant that we need to change.
Okay, we're having some technical difficulties with the phone bridge, so we're going to go instead to just one or two follow-up questions here at Houston.
Mark Carreau for Aviation Week. It's just a couple, one cleanup question on the ET numbers and the flight numbers. Could you correlate the tanks with the flights using the STS?
Sure. ET-137 is the STS-133 tank. ET-122 is the STS-134 tank. And ET-138 is the STS-135 tank. James, that reminds me, James had asked a question, do we think we flew with this before condition? That's important. It is likely that we flew on ET-136 with some of these stringers that had the low fracture toughness. We reviewed all of the information pre-flight and the information post-MECO, looked at that LOX flange, and it behaved absolutely nominally. But we don't know if we might have had a crack or two in those stringers. So yes.
For John, just as a curiosity, what was the astronaut office or actually the crew's response to these further modifications, and also what has been their training regimen through this? I mean, they were already ready to fly back last year, so how have they been staying proficient for whenever we get to fly on?
Yeah, well, I'll expand it beyond the astronaut office. We had no dissenting opinions on the plan as it was laid out yesterday, which includes the astronaut office, and they have a training regimen that keeps them up to date with their skills and the flight planning, and they do the commander and pilot do their shuttle training aircraft tests. They work with the EMCC doing simulations, so they're going to be ready to go.
Okay, I'm afraid that's all we have time for today. Thanks so much for participating, and you can find the materials from today's briefing online at the Shuttle website. You can see the full address there at the bottom of your screen. You can also, of course, keep up with future updates on nasa.gov. And coming up next on NASA TV, for those who are looking for STS-133 B-roll, we'll be playing the STS-133 mission overview. Tune back in tomorrow at 10 a.m. for our daily ISS update. And in the meantime, have a great day. Thanks.